Hello everyone, my name is Olivier. I'm Product Innovation Manager for Curamik Substrates and Coolers at Rogers Power Electronics Solutions. I am pleased to have you all on board for this webinar entitled Reliability of Metallized Ceramic Substrates for Power Electronics Applications. Please note that this webinar will be uploaded in our Design Hub within the next few days. You can follow the link indicated here, register into the Design Hub, and get full access to this webinar and other technical and product information. As a design engineer for power electronic systems, you require the selected power module to fulfill its electrical function as described in its datasheet. And you expect this module to be reliable, meaning that it should operate under given conditions in a defined period of time and within an acceptable failure rate. While solder fatigue and wire lift-offs have been the main limiting factors for the lifetime of conventional modules, new technologies for assembly and packaging of semiconductors have emerged, and new module generations achieve much longer lifetime. Looking forward, metallized ceramic substrates will remain key components in the modules to guarantee their functionality and reliability. After a short introduction, this webinar will give you an overview of the test conditions and test criteria to apply for lifetime prediction. I will then provide some guidance for the selection of the most reliable material combination and design of the substrate before we conclude this webinar. While assessing or specifying the reliability of metallized ceramic substrates, you will have to deal with 4 important topics. First, you will have to understand the test conditions that have been used by the manufacturer. Each manufacturer may use different test conditions, and you should better know the differences before you make any decision. Second, please make sure that the manufacturer has defined some criteria to judge when a first failure has occurred and by when the device in the test has reached the end of life. Third, you should get detailed information about the material combination that has been exposed to the test conditions mentioned beforehand. Not just the thickness of the insulating material and of the metallization are important here. Also, the technique used for joining these materials has a significant influence. And fourth, not every manufacturer will use the same design of the test vehicle, and you will learn in this webinar that reliability can be improved by design. Thermal cycling is the most common test method used for assessment of the reliability of metallized ceramic substrates. It is an accelerated test method and as such cannot give any information about the lifetime of the substrates in a real application case, but provides a good comparison between various substrates. The device under test is placed in a climatic chamber at a low temperature for a given duration and then moved in a second climatic chamber at a high temperature for usually the same duration. This represents one cycle, and this cycle is repeated many times till one can observe a first failure up to end of life. While almost every manufacturer of substrates will use the same test method, you should pay attention to the details as the test condition may significantly influence the test results. First, the transition time between cold and hot chambers can be very short in the case of thermal shocks, usually less than 10 seconds, or much longer, up to 5 minutes. In some cases, manufacturers may perform this test with 3 chambers to provide an intermediate plateau at room temperature. Second, the duration in cold and hot chambers may vary between few minutes up to many hours, but 15 to 30 minutes are typical values. Third, the minimum and maximum temperature, as well as the temperature difference between min and max values, can vary from one manufacturer to the other. In most cases, substrates will be tested between minus 40 degrees C and plus 125 degrees C, but one can find minus 55 degrees C up to 150 degrees C as recommended in some norms for military applications. Also, as the operating temperature of semiconductor devices keep on increasing, thermal test cycling may be performed with maximum temperature as high as 175 degrees C up to 350 degrees C, depending on the targeted application. Please note that any of these variations in test conditions will lead to different acceleration factors, and as a consequence, test results are no longer comparable. As an example, substrate with 0.32 mm thick zirconia toughened alumina ceramic along with 0.3 mm thick copper on both sides have been tested with different min and max temperatures. According to the probability plot, the calculated characteristic life, which is the time at which 63.2% of the units will fail, is 218 cycles when the chosen min and max temperatures are minus 40 degrees C and plus 125 degrees C. The characteristic life is cut in half when the temperature span goes from minus 55 degrees C up to plus 150 degrees C. This clearly shows that the chosen min and max temperatures and overall the test conditions largely influence the test results, and you should pay attention to that when specifying a lifetime for substrates. Temperature cycling ovens are available at Rogers, Germany, and we perform such cycling tests for internal purposes like process control or evaluation and qualification of new suppliers and new materials. On request, we can also conduct such cycling tests on behalf of our customers. Even though this is an accelerated test method, one cycle takes 30 minutes, and depending on the number of cycles still and of life of the device and the test, these tests can last for many days. So far, we've been speaking about the test conditions only, and you could see the influence of the test conditions on the test results. But you may wonder how to judge when a failure has occurred and when end of life is achieved. We will speak about the test criteria in the next slides, but before we do that, we should understand the failure cause and mechanism. Metal and ceramic have different coefficient of thermal expansion, meaning that these two materials do not expand and shrink at the same pace when they are exposed to temperature variations. As they are joined at very high temperature up to typically 800 degrees C for A and B or 1060 degrees C for DBC substrates, mechanical stress will be captured in the clad of material already during the joining process. Later, under real-life conditions, substrates will be exposed to significant temperature swings because the ambient temperature may vary and the junction temperature of the semiconductor devices will change as they switch on and off the load. This will cause alternating compression and tensile stress in the clad of material. This stress is not homogeneously distributed over the entire surface, but concentrated on the corner and edges of the copper pads, and ultimately will cause edge cracks in the ceramic, also well known as conchoidal fracture. Let's take a look now at the test methods and criteria that are typically used to assess the lifetime of substrates. The first method is to remove the samples from the climatic chambers after a given number of temperature cycles, etch copper away, and look for any cracks in the ceramic. For this purpose, a dye penetrant inspection is applied. This is a low-cost inspection method used to locate surface breaking defects in all non-porous materials like ceramics. Dye penetrant inspection is based upon capillary action, where low surface tension fluid penetrates into clean and dry surface breaking discontinuities. After adequate penetration time has been allowed, the excess penetrant is removed and a developer is applied to reveal the number and length of cracks. Of course, this is a destructive method, and the propagation of a crack for one and the same substrate cannot be observed as a function of the number of temperature cycles. But non-destructive method is based on the measurement of the resonance frequency. A test setup is shown in this slide on bottom left. A light knock on the top side will induce a vibration in the ceramic substrate that is captured by a microphone on the opposite side. For the specific test vehicle shown on top right, it has been observed that the resonance frequency decreases as cracks appear and grow in the ceramic. This decrease in frequency can be plotted as a function of the number of temperature cycles, as shown here on bottom right. However, this doesn't answer the question when the substrate has failed or has reached end of life. Comparison between frequency measurement and dye penetration test has shown that the decrease of frequency by more than 2% correlates with a significant visible degradation of the ceramic. This limit has been set as a threshold for failure for ceramic products in order to compare different kinds of ceramic substrates. However, this doesn't tell anything about the lifetime of a substrate in a power module because the conditions that would apply in a module are completely different. In a module, the substrate is populated with semiconductor devices attached on a base plate and encapsulated in a plastic housing or molded. As a consequence, copper and ceramic layers no longer have the freedom to expand and shrink with temperature variations as it is the case here. The inconvenience of this test method is that it works only for the specific test vehicle and therefore cannot be applied to any customer-specific layout. Also, it has been observed that the quality of the ceramic edge has an influence on the test results. So which other test methods could be suitable? Scanning acoustic microscopy is a well-known non-destructive test method for failure analysis. It employs ultrasound to penetrate solid materials and make visible image of defects such like cracks, delamination, and voids. This investigation process is repeated in a systematic pattern until the entire region of interest has been scanned. As a result, an image of the substrate is generated. The contrast on the image highlights the location of a defect. At time 0, we don't see any defect. But after some temperature cycles, the change in contrast indicates that the formation of cracks has started and that the cracks are propagating until a significant degradation is achieved. However, there is no detailed and accurate definition by when a degradation in the substrate can be classified as significant. Basically, degradation in the substrate should not impact the heat dissipation from the chips, but this depends on the position of the chips relative to the degradation. As a consequence, this visual assessment leaves much room for interpretation. The most promising approach to define the progress of a degradation is to measure the delaminated copper area as a percentage of the total metallization area. This requires a very good and consistent resolution of the image. Note that the resolution of the image is limited either by the physical scanning resolution or the frequency of the sound. This also requires an adequate equipment and software for image analysis. At Rogers, we keep on improving the quality and consistency of acoustic images, and we have now suitable equipment and software for image processing. On this chart, the delaminated area for various suppliers of alumina has been plotted as a function of the number of temperature cycles. Once again, it is difficult to give a good definition for end of life, and we may set the threshold at either 10 or 20%. But we can see from this graph that the cracks occur and propagate at different rates depending on the suppliers. This is a very good tool to compare existing materials or suppliers and for the qualification of new materials or suppliers. We have seen that it is very important to be aware of the test conditions and test criteria used for the assessment of the reliability of the substrate, as they can tremendously impact the test results. Now, we would like to understand which are the possible measures that can be taken to increase the reliability of substrate. Maybe the most important factor is the selection of the material and particularly the choice of the ceramic. This slide, you see data taken from Rogers design rules. The high thermally conductive aluminum nitride would be the best choice for the purpose of heat dissipation, but it unfortunately shows poor mechanical properties, and as a consequence, aluminum nitride DBC substrates are prone to fail after few temperature cycles. Alumina DBC substrates are more robust And even though the thickness of the alumina ceramic is only 0.32 mm compared to 0.63 mm for aluminum nitride, they can survive almost twice as much cycles than aluminum nitride DBC substrates. Once doped and reinforced with zirconia, alumina ceramics have improved mechanical properties and can last for up to at least 110 cycles in the given test conditions. Silicon nitride ceramics are not shown on this graph, but are tougher than the ceramics mentioned beforehand. Once joined with copper by active metal brazing, silicon nitride substrates can survive more than 1000 cycles. The lifetime of substrates also depends on the thickness ratio between copper and ceramic. Generally speaking, a thick and strong ceramic substrate, metallized with a thin copper layer, is expected to withstand much more cycles than a thin and fragile ceramic substrate with a thick copper metallization. Those thicknesses are usually designed to achieve the required insulation, heat dissipation, and current density, but you should be aware that the best electrical and thermal design is not likely to be the most reliable. A trade-off will be required, and this trade-off may not always be the same for the different applications, as requirements and mission profiles are likely to vary. The main concern with material selection is that it often has a cost impact, and it is not surprising that the most reliable materials are not the cheapest materials. Luckily, there are other options to increase the reliability by design and without adding significant cost to the solution. As a first example, we will speak about dimples here. Basically, dimples are holes in copper metallization. Curamik has developed a proprietary dimple design for the purpose of thermal stress relief. The objective of such dimple design is to reduce the copper thickness on the edge of the copper pad and hence increase the lifetime by reduction of the thermomechanical stress in these areas. Customers may design in dimples with 1 or 2 rows on the edge of the copper pad and on both top and bottom sides. Dimples can be either completely edged through the copper till ceramic is visible, or only partially edged. In this case, the depth is typically more than 1/3 of copper thickness. Design rules, shown on this slide, provides guidance for the designer of DBC substrates. Diameter is given here for completely edged through dimples. Dimples do not directly add cost but they require additional area which is not available for die attach and wire bonding. But how do dimples act as stress relief? This is the result of the mechanical weakening of copper by removing it partially. This means that there is less copper material applying compressive forces which are critical for the ceramic. Finite elements modeling shows that there is an almost linear decrease of the stress in the ceramic for increasing dimple depth. This effect can be observed on the acoustic images for 0.6 mm thick copper bonded on 0.32 mm zirconia toughened alumina with and without dimples. In both cases, substrates do not show any degradation after 20 cycles. After 40 cycles, substrates without dimples are completely delaminated, while substrates with dimples look much better even though degradation has already started. Another parameter that has an influence on reliability is the etching ratio or etching flank width. For one and the same copper pattern according to drawing, one might increase or reduce the etching time to guarantee that the distance between copper tracks will be sufficient for the purpose of electrical isolation. For thick copper metallization, as opposed to thin layers of copper, a steep or tapered etching flank can hardly be achieved even if you would reduce the etching speed and increase the etching time. Anyway, etching the parts longer may not be a good idea. As you increase the etching time, the side walls of copper pattern will become shorter and shorter, and this leads to even more stress concentration at the edges of copper pads. A study was conducted at Rogers for a standard material combination. Results indicate that there is almost a linear correlation between the average flank width and the number of temperature cycles. According to our design rules, the flank cannot be larger than half the copper thickness. For 0.3 mm copper thickness, it can be max 0.15 mm, and it should be as close as possible to this value to guarantee the best possible reliability. In this finite element modeling, the edge angle was varied between 10 and 100 degrees for a DBC substrate without any dimple. From 10 to 62 degrees, stress is increasing, and from 62 degrees, a slight decrease can be seen before the values converge. The increase is again due to the fact that the more copper exists, the higher the compressive forces upon the ceramic parallel to the copper-ceramic interface will be. This means that the most important property preventing the DBC ceramic from the failure of conchoidal cracking is that the etching angle of the copper end tail is as small as possible. The most important method to prevent the ceramic from cracking in the vicinity of the copper tail is to decrease the stress intensity by a small copper tail etching angle. This may be even more efficient than dimples and should not consume as much area as dimples. Another important design issue is to equally balance the stress on both sides of the ceramic substrate. It is recommended to have same copper pattern and same copper thickness on both front and back sides. As backside is mainly plain copper, copper should be removed on component side only where and when necessary. For instance, to fulfill the requirements regarding electrical isolation between copper tracks and between front and backside. Particular attention has to be given to the copper-free perimeters. The difference in copper-free perimeter between front and backside should be 0.5 mm or less in order to balance semi-stress and thus avoid the generation of crack. Recent observation was that an additional coating on the copper edge can significantly improve the lifetime of substrate. In this example, with 0.6 mm thick copper, dimples can hardly help to increase the number of temperature cycles. After 60 cycles, almost all parts are showing visible and significant degradation. The same substrate from the same batch, but with an additional coating on the edge, do not show any damage after 400 cycles, and a degradation becomes visible after 600 cycles. This is a huge improvement, and in-depth investigations will be conducted to better understand the mechanisms that are preventing from crack formation and propagation. Another way to increase reliability is again a design issue, and particularly the design of the corners of copper pads. The aim of a former study conducted at Rogers was to compare two identical layouts with sharp and rounded corners. The single units were arranged on a master card as shown on this slide. The acoustic images show that all parts, irrespective of their shape, have survived 50 cycles without any visible degradation. After 60 cycles, degradation is becoming visible for the substrate with rounded corners only. And after 70 cycles, this substrate is severely damaged, while degradation is starting for the substrate with sharp corners. In the scope of that study, we have also analyzed different ceramic suppliers. Here, after 60 cycles, the degradation of substrates with rounded corners is much more advanced than with sharp corners, irrespective of supplier. But the severe damages with supplier X cannot be observed for supplier Z. Same observation can be done after 70 cycles. The source of supply and quality of the ceramics has a tremendous influence on the reliability of substrates. To secure business continuity, multiple sources of supply are necessary. Rogers has been investigating many sources of supply and only qualified a few that deliver good and consistent quality to guarantee the best possible reliability. To conclude, I would like to show once again this overview. As test conditions and test criteria are likely to be slightly different for each substrate manufacturer, it may be difficult to specify the lifetime of substrates in a very generic way. Today, the lifetime of power modules is not limited by the substrate, and there are still many ways to design robust modules with existing substrate technologies. The selection of the material is the very first and most important step. A good knowledge of your application and its mission profile is required to select the best possible material at the lowest cost. And by some design tricks like dimples, etching ratio, edge coating, and corner design, you can easily work around some potential reliability issue and make the best usage of the available substrate area to reduce cost. So I hope I could give you a good overview about the aspects to consider when specifying the lifetime of substrate, and that you now understand what can be done to further improve the reliability of substrates. Thank you for your attention. The session is now open for questions.